Okay, so the first topic we're going to have a look at is known as atomic structure. In chemistry, by now, I'm hoping that you have learned that the atom contains a positively charged nucleus made up of protons and neutrons, the protons being positively charged and the neutrons having no charge or being neutral. Round the outside of the nucleus, we have free moving electrons that kind of circle the nucleus. These electrons are negatively charged. Now, where did this idea come from? How did we know, or how do we know, that atoms are this way? Well, a very long time ago, a scientist called Ernest Rutherford was basically the discoverer of what the nuclear atom looked like. Well, actually, it was his students, but he took credit. So the structure of the atom. We believe the atom, as I've said, has positively charged protons and no charged neutrons, which can be found in something called the nucleus. Inside the nucleus, there are very, very strong forces of attraction. Around the nucleus, we have our electrons. So proton, positive charge, neutron, no charge, and electrons on the outside have a negative charge and very, very little mass. In terms of atomic mass units, the proton and the neutron have 1. Now, before we get into Rutherford's scattering experiment, what do we mean by an unstable nucleus? Well, down the bottom 2 rows of the periodic table, we have elements that are by and large deemed unstable. You will have things like uranium, plutonium, strontium, amongst others. What does that mean, that they are unstable? It means they will give out alpha, beta, or gamma, or perhaps even more than a combination of those, and it will change into another, more stable element. So we're going to learn later that, if any unstable nucleus gives out alpha, beta, or gamma, it will eventually change into something else. This is what we mean by unstable. Eventually, a radioactive isotope will become almost 100% stable. But for the purposes of IG, we can regard it as stable. Let us now have a look at Rutherford's alpha particle scattering experiment. What's going on here? Now, at the right-hand side, the blue rectangle represents a Geiger-Müller tube, which you will learn more about in another PowerPoint. To the left-hand side, we have an alpha radioactive source. This radioactive source is giving out alpha particles, and you'll learn more about alpha later, but basically alpha is a helium nucleus. It's surrounded by lead shielding so that we can force the alpha particles to go in one direction towards the Geiger-Müller tube in this drawing, past gold foil, if indeed it goes past gold foil. So in the middle here, we have our little bit of gold foil. Just think of tin foil, but it's made of gold. And this is all taking place inside a vacuum. Later, you're going to learn that alpha is very ionizing. This means that it knocks off electrons of anything that it comes into contact with. The idea of this experiment is to see the structure of an atom. To do this, we're deliberately going to do the experiment in a vacuum so that the alpha particles can only interact or interfere, if you like, with the gold foil and nothing else. Because if we didn't have a vacuum, we would have air, and that would not be helpful in this experiment. So, what happens in this experiment? Well, what you'll find is the vast majority of alpha particles pass through the gold foil. Now, think about what the gold foil is made up of. Gold will be made up of atoms. The atoms have a nucleus, and around the nucleus we have electrons. So this gold foil is made up of billions and billions of atoms. You're going to learn much more about alpha, as I said, later, But an alpha particle is basically a helium nucleus. So what you're really doing is you're throwing something as big as a nucleus at a piece of foil that's full of lots and lots of nuclei. Okay, because if you think about the largest part of an atom, it is the nucleus. So relatively speaking, you're taking the biggest possible particle you can and you're firing it at a piece of gold foil, which has, we think, or we did think, many nuclei that are just as big, if not bigger. So why do most of them go through? Well, let's imagine I asked you to go fishing with a fishing net, but the holes in the net were as big as me. Now, I'm about 6'2" tall, and I'm not sure how wide I am, but you know, that would create big holes in the fishing net. I hope you understand then that I wouldn't catch many small fish because they would slip through the holes. Well, basically, this is what you're going to find out is happening here. So right now, let's just focus on the results. Most of the alpha particles will go straight through this gold foil. A few of them deflect or bounce off to the side, and even fewer bounce back. So let's just say you had like 1 million particles. You'd have the vast majority of them, like 900,000 of them, going straight through. You'd have maybe 50, 60,000 of them bouncing off to the side, and you'd have even fewer bouncing back. What's going on there? Well, what you're going to learn is Rutherford concluded that the atom is mostly empty space. Here's a variation of that experiment that basically leads to the same conclusions. We're not using a Geiger-Müller tube here, we're using a zinc sulfide screen. Now we're still firing out alpha particles, we're still doing it in a vacuum, we're still firing it at gold foil, but instead of a Geiger-Müller tube, we've got this screen in the background. Now, what does this screen do? Well, it's quite similar to when you were a child and you maybe wrote something in white ink and you maybe brought UV light over the ink and it produced a word. It's a very, very similar concept. Basically, the zinc sulfide screen will light up when the alpha particles hit it. And as you can see in this experiment, the vast majority, again, are going straight through, some deflecting a little, some deflecting quite a lot, but very few are bouncing back. So what did Rutherford think then? Here is a diagram of what he thought. Here we have our gold foil. The big golden circles represent the entire gold foil, and those kind of reddish dots there, they represent the nuclei inside the gold foil. Why did most of the alpha particles pass straight through? Because Rutherford basically concluded that the atom must be mostly empty space. That yes, there's a dense nucleus, but round about it, there's pretty much nothing. It's a bit like me asking you, let's say you were Superman, and you're outside of our solar system, and I asked you to throw a rock that's as big as the Earth into the middle of our solar system randomly. I hope you understand that the solar system is very, very big. We have the sun in the middle, which we can regard as our nucleus, and we have the planets orbiting the sun. But in between there is lots and lots of empty space. So in similar vein, Rutherford concluded that the atom must be mostly empty space because many of the alpha particles pass straight through. A few of them bounce off to the side. They deflect. Notice that they don't hit the nucleus themselves. That's because we're going to discover the nucleus is positive, as is the alpha particle. And positive will repel. But why did they kind of deflect or bounce off to the side? Because they were coming close to something dense. What is that dense thing? It is the nucleus itself. So a few alpha particles got deflected a lot. They came close to a nucleus which repelled the positive alpha, so the nucleus itself must be positively charged because it didn't actually hit the nucleus. Very few particles, alpha particles, bounce straight back. Notice once again that it doesn't hit the nucleus, it just bounces off. Now, in reality, if it goes straight at the nucleus, it should come straight back, but many books and diagrams show it going off slightly to the side so the student completely understands that it was bouncing off. What did Rutherford conclude? Hardly any alpha particles bounced back. They hit the nucleus and bounced off it. The nucleus is small, dense, and positive. How do we know it's small? Because very few hit it. How do we know it's dense? Because it was the alpha particles that bounced away. The gold stayed where it was. How do we know it's positive? Because it didn't actually hit the nucleus itself. So here's an example of what we think happens around an atom. So in the middle, we've got a positively charged nucleus made up of protons and neutrons, and the orange dots here represent electrons. If we have a particle that's very far away from the nucleus, nothing happens, it just goes straight through. The closer it gets, it starts to deflect. Now remember, alpha is positive, the nucleus must be positive because it's repelling. The closer it gets, the more it deflects, the more it bounces off to the side. And if it goes straight at it, in reality, it should bounce straight back. But we show this little angle just to make it clear to you that it's bouncing off, rather than doing a line back on itself. So Rutherford's conclusion then. Here we've got some gold atoms spread out randomly. I know it looks red, but round the red stuff is representing the rest of the atom surrounded by electrons. As you can see, the kind of black arrows, the lines, they represent alpha particles, and most of them go through. A few bounce off to the side, and even fewer bounce back. Rutherford said that the nucleus was very small because very few alpha particles hit it, that it was positive because it repelled from the nucleus, it didn't actually hit the nucleus. It was heavy or dense because it was the alpha particles that bounced off to the side or bounced back, whereas the gold itself didn't move. So based on this, this is what we believe the structure of the atom is. In the middle there are red positively charged protons, are blue no charged neutrons, and round the outside electrons. But clearly in reality, an atom is 3 dimensions and not 2. I wouldn't really worry if you don't understand this, because in most subjects, it's represented as 2 dimensions.